in this video I'll quickly go over the past paper questions 3, 4 and 5. So question 3, first of all, let's read what the question says. Magnesium nitrate decomposes. So you can see they're talking about decomposing on heating according to the equation, so it's given us an equation. And then you'll see that the question works through asking relative formula masses, getting you the number of moles, and then at some point they'll ask you to work out the amount of a substance produced from that. So with the equation, remember the first thing is look at that ratio. So every 2 magnesium nitrate will produce 2 magnesium oxide, 4 nitrogen dioxide, 4 NO2s, and 1 O2. Now, we're going to see later on in the question, it's this ratio here, the 2 to 2 ratio is the one that we need for this question. So 2 to 2 simplifies down to 1 to 1. Okay, so the question guides us through. So the first one asks, what's the relative formula mass of MgO? So that's fairly simple, just add 24 and 16, 40. For magnesium nitrates, MgNO3. Now let's do what's inside the brackets first. So nitrogen is 14, 3 oxygens would be 16 times 3, so 3 16s would be 48, plus 14 is 62. So there's our 62. And then there's 2 of those. Remember, we've bracketed it and put a 2 outside of it, so 62 times 2, and then add on the magnesium, 24. So 24 plus 62 times 2, 148. Then use your answer to calculate the number of moles of in 5 grams of magnesium oxide. Now, we'd worked out here that 1 mole of magnesium oxide was 40, so just keep it going with the right place there. So N equals M over RFM, so 5 over 40, 0.125 mole, or 1/8 of a mole. Now, we're going to carry that number of moles forward. So use your answer in part 3, that was that 0.125 moles, to calculate the mass of magnesium nitrate required to be heated to produce 5 grams of magnesium oxide. Now, there's the ratio, so we know that we've got that number of moles of magnesium oxide, 0.125. The ratio of that back to the magnesium nitrate is 2 to 2, or 1 to 1. So the ratio of magnesium oxide to magnesium nitrate, 2 to 2, or more simply 1 to 1. And that means 0.125 mole of magnesium oxide needs 0.125 mole of that to be produced, because there's a 1 to 1 ratio, you need the same number of moles. The mass of 1 mole of MgNO3 we had worked out earlier on, 148. So remember going back up there, yeah, so there's our magnesium nitrate, 148. So let's put that back up. So 148 for MgNO3 2. So therefore 0.125 mole of magnesium nitrate is going to be 0.125 times 148, 18.5 grams. So there's our answer. The next one asked for the percentage yield. Now it says when the reaction was carried out, only 4 grams of magnesium oxide were produced. Now you remember the equation for percentage yield, I'll put up on the screen in a moment, was the actual yield. Well, there's the actual yield, there's how much we actually got, 4 grams, divided by the theoretical yield. Now how much we were trying to make? Well, if you look back up here, it said required to be heated to produce 5 grams. So there's a theoretical yield, there's what we really thought we were going to get. So we hoped, or theoretically, we're going to get 5 grams, but we only got 4 grams. So therefore the percentage yield is going to be the actual mass, 4 grams, divided by theoretical, 5 grams, times 100, which is 80%. Why do we not get 100%? Well, you remember when you transfer things, if you put one container onto another, you get a wee bit sticking, so lost during transfer from one container to another. The magnesium nitrate can sometimes have those side reactions, can be converted into something different other than magnesium oxide. And then the other one was that theoretical thing was called equilibrium. The reaction doesn't go to completion, that the products can turn back into the reactants. So that's the other one. So any 2 from that list would give you the 2 marks if those came up. Okay, question 4. Again, if we look at the question, this question is about how much iron 2 oxide will be needed to produce a certain amount of iron sulfate. So there's our iron oxide, there's our iron sulfate. Can I draw you down to this? Relative formula mass of FeO is 72. Now, lots of you would sometimes when you're in the middle of calculation go and calculate again. So they've tried to help you a wee bit. They've given you one of the relative formula masses, and then you'll see down here you're asked to work the next one out. Now, let's do our usual thing, get our ratios. So if you look at the equation, there's no numbers in front of it, so 1 to 1 to 1 to 1 ratio. Then we're asked for the relative formula mass of FeSO4. Well, FeSO4, again, use the atomic numbers there, 56, 32, F and Fe and S, and then 4 oxygen, 16 times 4, so 152. Then use this to work out the number of moles in 7.6 grams, so N equals M over RFM. So 7.6 divided by 152, and that works out 0.05 mole. Then use the information in part 1 on the equation and the moles that we've just worked out there to calculate the mass of iron oxide needed to produce 7.6 grams of FeSO4. So we'd worked out on the previous bit of the slide there, just up above in your question, that was 0.05 mole. There's a 1-to-1 ratio. Do you remember we saw that with the ratios earlier on? So for every one of these, you need one of these. So 1-to-1 ratio FeSO4 to FeO. So 0.05 mole of FeSO4 needs 0.05 mole of FeO. And then to get the mass of it, 1 mole of FeO, 72. That was in the question, remember, at the start. And therefore 0.05 mole is going to be 0.05 times 72, 3.6 grams, and that's our answer. And the last part of the question, now the final answer is actually very simple, 1. I'll show you the working out the logic behind it. So there's a 1-to-1 ratio of iron oxide. So if you mixed 1 mole of this, it was 1 mole of the iron oxide. So if you mix 1 mole, so there it says 1 mole of iron oxide. So if you mix 1 mole of this with 2 moles of this, now that's a wee bit like, do you remember those examples we did when we started this of making the potted plants where you needed the pots in the plant, you need 1 pot for each plant. And if you had, for example, say 100 of these and 200 of those, so if you had 100 plants and 200 pots, then it was the lower number that really determines how much you can make. Remember that you've got an excess of the other, you'll have some left over, you can't use those. Now this is the same sort of thing. So what they have here is 1 mole of this. So there's 1 mole of this, but 2 mole of this. Now what that means is that 1 mole of this could react with 1 mole of this. So 1 mole of FeO can react with 1 mole of HSO4. So that's all that we can get used up. So the answer is 1 mole. This one, again, you'll see what makes this a little bit different, and they, again, deliberately do these sort of things just to challenge you. You'll see that the actual formula looks a little bit funny, can be worked out in exactly the same way we've done before. NH4 is in brackets. Now we don't have to multiply it by anything, we can total up what's inside the bracket, H2PO4. And what you're asked is that this is ammonium dihydrogen phosphate, can be made by the reaction of ammonia, this, with phosphoric acid, this. And again, you can see that they've told us some information down in the question. So we'll point that out there before I cover it up with the ratios. NH3 is 17. So we'll use that down here in the question. So ratios. So although they've given you a complicated formula as the product there, it's 1 to 1 to 1. They have asked to do the 2 relative formula masses, so we'll do those quickly. H3PO4, 1 times 3, plus phosphorus, 31, got it there, plus 4 oxygen, 16 times 4, 98. So 1 mole of H3PO4 is 98. And then 1 mole of this is going to be, well, inside the bracket, NH4, 14 plus 1 times 4, 4. So 14 and 4 would be 18. So that 18 is what's inside the brackets. 2 times 1, 2 hydrogens, phosphorus, 31, and then 4 oxygen, 16 times 4, so 115. Then the chemist reacted 6.8 grams of ammonia with excess phosphoric acid. So what they're saying is that you don't have to worry about the phosphoric acid in the calculation. There's more than you need, and that guarantees the reaction takes place. So we've got the 6.8 grams of ammonia. So we were told up here, it's been covered by the 1 there, but that ammonia was 17. So N equals M over RFM, 6.8 over 17, 0.4 mole. Then this asked how many moles of phosphoric acid are needed. Well, the ratio of ammonia to phosphoric acid was 1 to 1. So 0.4 moles of ammonia reacts with 0.4 moles of phosphoric acid. So the answer is 0.4. And then calculate the maximum mass of ammonium dihydrogen phosphate that could be made from 6.8 grams of ammonia. Now, if we go back to the equation, you remember our ratio was whatever ammonia you have, and it worked out here it was 0.4 mole. You make the same amount of this. So the answer is going to be 0.4 mole of this is made. So going back to it, ratio of ammonia to that ammonium dihydrogen phosphate is 1 to 1. So therefore 0.4 moles of ammonia produces 0.4 moles of that NH4 H2PO4. Now to work out the mass of it, remember 1 mole we'd worked out was 115. So 0.4 mole is going to be 0.4 times 115, 46 grams. And then it says, if the reaction was carried out, 30 grams of ammonium dihydrogen phosphate were produced. What's the percentage yield? Well, there's the theoretical yield. So we've just worked out theoretically, we could have got 46. Actually, we only got 30. So actual over theoretical. So 30 divided by 46 multiplied by 100. And that to one decimal place is 65.2. You could leave that as 65%, but usually we leave our percentage yield to one decimal place just to be sure. Okay, so that's the 3 questions. So you're now free to look over and do the last 3 questions. Again, similar type of calculations. All have got slightly different ways that they ask them to go down, but they do try to guide you through the question. So use one step to go into the next one, to go into the next one, and go through. And then you can send me through photos of that, and I'll take a look at it.